My name is Bill Bereza. I work with Atomic Object. We're in Grand Rapids, Michigan. And I'm going to be talking about some work we did with embedded development, using Ruby to help the embedded development. So what is it that I'm actually going to be talking about? It's going to be involving an embedded C project on an 8-bit PIC micro. I'll go into some more details about the specific processor we used. But it's basically a pretty small system. How did we do this project and how did Ruby help? First off, we used Rake. Basically, I just decided I want to use Rake on this project. This project started out as just a regular C project. I hadn't even done anything with Ruby before I started this project. And I just wanted to use Rake as the build system because I was tired of using Make and didn't want to use Ant. So Rake was something that people were using in the office on some other projects, and I thought I wanted to try it with a C project. Using Rake then sort of led to Argent being involved. Argent is basically a way of having Ruby code embedded in files get processed. We had unit tests, just regular unit tests written in C, but these tests used mocks that were generated by a Ruby script. Our system testing was all done in Ruby with some help from some C extension libraries. And we used a continuous integration system in Ruby. So why? Why did we do this? Well, in the beginning, programming basically required some very detailed knowledge of the machine that you're working on. I'm talking back, 60 years ago. You had to know the details of the hardware that you're writing for. Computers weren't very powerful, and tools available were pretty primitive. And there was a lot of pain when it came to doing software development. So programming was not, always fun. So people, tried to find better ways of doing it. So along came compilers, languages, and libraries that would help make the process of development easier. That helped some. And today, we have things like automated tests, code generation tools, domain-specific languages, continuous integration, spec tests, a lot of things that help make programming a lot more fun and easy. But there's a problem. Embedded devices. They're still a lot like the old computers were. They're small, cheap, and they're everywhere. But the problem is, they are everywhere, and they all have software, and that software has bugs. And when you have a process of development that involves a lot of hand tweaking, a lot of having to worry about the details of the hardware you're writing for, bugs are easier to introduce and harder to find. This is sort of a brief overview of how embedded development is generally done in most places. Somebody writes some code, they flash that code onto the device, they fiddle with the device, plug stuff in, hit some buttons, maybe put a scope on it, try and debug the problems they had, look at the scope again, and try this all over again. This kind of process is unrepeatable. It generally involves someone who knows what the system hardware should be doing and can look at it, but then you've basically got the expert is the system test. This leads to the development process involving hope that you can get things done right, anger when things don't work the way you expected, and fear when you have to make a change to the system. So the goal for our practice at Atomic Object is to apply good practices. These practices involve automation, unit tests, system tests, user stories, behavior-driven development. We've been using RSpec lately on all our Ruby projects. And although this project that I'm talking about was one that was started about 2 years ago, and it's basically when I was learning Ruby, so we didn't use anything like spec for the tests. These are basically unit tests, usual doing the assert equals kind of things. Mocking is something that I think the more I've done it, the more I'm going to want to keep doing it every project. I think it really makes not just the code better, but it drives the design of the code. And that's, I think, the big thing about using mocks in your system. You see behavior patterns in your code. And continuous integration. Things don't stay broken for days at a time. The problem with all this is that vendor tools suck. They're basically written by the vendors to sell their hardware. They aren't in the business of selling development software. Chip vendors that provide IDEs generally provide very simple IDEs, and they also don't really do what you need, like test and automate development. They provide a lot of great debugging tools, and they make a lot of money selling debugging tools because the tools they provide you to write software don't help you or let you make well-tested software. So the solution to this problem that we had when we started this project was Ruby. And tools written in Ruby, which provide the glue that put all these good practices that we want together into our system. The project that I was working on was a development project for automated guided vehicles, which are self-propelled, semi-autonomous factory vehicles, which basically look something like this. They generally drive around a factory, usually with a fixed route, but they have a set of planned stops along that route, and the vehicles themselves will drive themselves to and from each point along the way. Usually they'll stop at some place, wait for load to be either placed on top of them, like in the case of the vehicle on the right, or the vehicle on the left there would drive to a location, hook itself up to a trailer of some parts, and then drive to another location where those parts are delivered. And there's other basic types of vehicles. There are automated forklifts, tow vehicles. The unit load carriers is what the vehicle on the right was. And just basic carts, which are, they just drive themselves around and have something put on top of them. All of these vehicles that we were working on for this customer had a shared hardware architecture. So basically what it meant is that there were a set of configurable boards for each vehicle that were shared among them. So some of the systems that the boards did were steering, speed control, monitoring the batteries, and navigation. Our first project for this customer involved doing the speed control board. But I'm not going to talk about that one because that was sort of where we started using a few of these practices, using a little bit of Ruby, but we really fine-tuned them in our second project, which was the battery monitor board. Here's a picture of the actual board itself hooked into our test rig. It's basically a PIC microcontroller, some regulators, a few support chips, and a lot of inputs and outputs. This project was using an embedded C. It was basically a subset of ANSI C. It's actually the IAR compiler, which is a company that provides embedded development tools. And this customer basically, this chip that we're using, the microchip PIC18F2480, is not a very powerful system. It has a top CPU speed of 40 megahertz, 16 kilobytes of flash, which is just the program memory, not RAM, and 768 bytes of RAM. And this is the environment we had to work in, and we wanted to be able to do all of those processes and practices that we would normally do in any desktop or Rails application. So how did Ruby help? As I said, the first thing I did was I wanted to use Rake. Rake was basically sort of the wedge tool that brought in all the other Ruby things that we wanted to try. So we had a rake file that had basically two different targets, rake test system and rake test units. And our normal process would involve doing the system test first, which we'd write in Ruby. For these tests, we used a library called Sister, which is a system testing framework that we've developed in-house. Carl and Fox from our company actually presented presented here 2 years ago, I think, about the Sister framework. Here's an example of a specific system test. So basically what this test is doing is, this is just one test out of probably about 24 different tests, where we are using a communications bus called CAN to talk to the board. And what we want to do is verify that the board is reporting the battery level. The battery level for this vehicle is basically reported as a number from 0 to 9 onto this CAN bus. And there's another computer in the vehicle that is looking for that battery level message. And then when the computer sees the battery level at 0 or load is, at a certain threshold, it'll tell the vehicle, drive to a charging station and charge yourself up. So what this is doing is first configuring the board itself, telling the board that it should be reporting the battery level using an instantaneous report. This board can do like an averaging mode over time or instantaneous battery level. Telling the board to report into the normal Canvas format. This board, one sort of strange thing about this is that this board was a brand new board, which was a redesign of an existing board, and they wanted to have this board actually be able to plug into old vehicles, which meant you had to be able to configure the board to talk in the old formats that old vehicles wanted to use. And then we configure the battery to basically say it's the type of battery it is, which is I think it was 700 amp hour battery, 24 volts with a flooded cell type, which basically tells the board then to how to interpret the voltage levels it's getting from the battery. Basically, the board just uses a lookup table inside based on the battery parameters, and it knows based on the voltage there's a certain curve over time, and it can say how much battery life is left. So then basically the board, our system test would then pretend to be the battery and report that that the vehicle is consuming 40 amps of current, and that it is consuming the current and not charging it. And then we say what the battery voltage is reporting, and based on basically the two inputs are current and voltage, and the board then is able to calculate how much life is left in the battery. So you can see in this test here, battery voltage of 24 is about, the battery life is actually about half full. When the battery is completely full, it's actually reporting more than 24 volts. And then when battery reports voltage at about 22 volts with 40 amps of current being consumed, then the battery is dead. Battery is basically, its life is dead. Whether the battery actually can have enough energy to drive the vehicle is probably true. As far as the board is concerned, the battery has no life left. And the purpose of these system tests were that we could have the customer who was the engineer, who knew what the vehicle should be reporting, he was able to read these tests and understand and tell us, yes, this is correct. He was able to give us specific points of data and what those things should be reporting. The actual lines in the system tests are function calls into a driver file. Sister uses, you basically write a driver file to wrap to, your long sort of DSL type function calls go into the driver and actually do the communications with the board. Here, when you set the battery voltage, we're using a library that we wrote called Minilab, which I'll go into a little more detail later, which will, set a specific pin to a certain value and an analog input on the board. But the user never had to care about these details when they're looking at the system tests. So we used Ruby C extensions for this. The first one we wrote was for the Minilab. The Minilab hardware is basically a digital analog I/O board. that connects via USB to the computer. So we wrote a Ruby class that provides a couple of basic functions: read analog, write, read digital, and write digital. And the box is then hooked to the board and to the PC. The second Ruby C extension I wrote was for a device called the PCAN, which is basically just a CAN bus to USB converter. CAN bus is the communications format that's normally being used on these vehicles. Internally, the vehicles use CAN bus between all the boards. There's usually about half a dozen boards in the vehicle. There's, doing things like the main central computer will tell the steering board to turn right, a certain degrees for a certain length of time. It'll tell the speed board accelerate to this speed over this delta time, and then it'll also be looking for the battery level report and doing things like driving to the battery charging station. One thing the battery board also does is when the vehicle is actually charging itself, the battery board recognizes that and is able to then tell the computer when the batteries are fully charged, and then the vehicle will leave the charging station and drive on and continue its work. So we use the CAN in system tests to basically simulate the system. As far as the board is concerned, it's running live in the actual vehicle. The board is running the actual firmware that will be going in the vehicle, and the board doesn't know it's not in the vehicle. It's just acting as if it's inside a vehicle. And the PCAN Ruby class we wrote basically provides message methods to send and receive CAN messages. Some just pretty basic, C extension libraries. So for continuous integration, we have a build service set up that's always connected to these two USB devices and via that to the board. Here's sort of an overall diagram of what the system looks like. And it also sort of drives you through what is actually happening when we run a system test. So it compiles all the latest code checked out from SVN, burns it, flashes it onto the device, uses the Minilab hardware, which is the black box in the center there, to make it look like there's a battery with certain voltage, make it look like, there's other inputs and outputs happening, and then read what the level is being reported from the board via the PCAN, which is the little box at the bottom, and basically then verify that we're seeing what we should be seeing. So these are basic black box type tests. For our system tests, we're not looking at the details of how the board actually does anything. It's really just looking at the inputs and outputs from outside the board. And our other rate target we had was a unit test written in C. We wrote a little C test library called Unity. The reason for that was it had to be something small enough. We found CPP unit was way too big for what we needed. We actually could have tried switching to a C++ compiler for this project, but that would have left us very little memory left over in this board. This board specifically needed need to use quite a bit of the available program memory to do things like have the lookup tables for all the different types of batteries that it could support. So we had to write our own unit test library. It just basically does simple things like provide assert equals, and it's basically just one .h file is what it started out as, with just a bunch of macros, and stores results in a global variable and a struct that gets checked at the end of the tests, which is a little crude to set up. It's not like JUnit or anything like that. It doesn't really provide much support for setup and teardown of the test, which is something that we then used Argent for. Rather than actually writing a good unit test library that could do a lot for us, we used Argent to actually generate C code, so we didn't have to write a lot of the tedious unit test code. Argent would do things with it for us. This is sort of what Argent, the code gets inserted into the C file to have Argent calls. Basically, having Argent, load a Ruby file, call a function, and then the outputs get spit into your C file. And what we did for our test was the argent function would actually go through the test C file that is being parsed, find all the functions in there, and insert C code. We would insert for each test file, it would actually generate the main for the C code, which would call all the different unit tests. And it would actually look through, we had a naming convention where it was test something for all our test functions. And for this system too, we had every unit test compile it into its own executable just because that was the biggest we could actually fit into the board when you combine the unit test library with the code being tested. The other thing we did, which is the sort of the first really big use of Ruby in this project besides using rake, was something at one point I called it super mock. I think the function's still in there, but basically a mock generator for C. And what the argent call does is basically initializes these mock functions or mock classes that we created for every C file in the system, except the ones that you actually want to pass in. So what we would normally do in our unit tests is, except for the specific file you're testing that's under test, everything else on the entire board was a mock. So basically we mocked the entire universe and this board except for the individual files and individual functions that you're testing in your unit test. And to do that, and to make that easy and possible, we had a script that generated all the mocks. It's called CMock. We're actually in the process of releasing it on our website. I actually haven't been using CMock in about a year now. There's a couple other guys in our office now who are working on a current embedded project, and they've made some enhancements to CMock, and they're going to be releasing that. I think it was supposed to be real soon now, is what they said. So any day, maybe Christmas. And so what this does basically is just a quick Ruby script that I wrote up. Actually, it was at the beginning of this year. I wrote this when I was at a conference that I won't mention because the conference was so dull that I basically spent all my time writing this Ruby script instead. And you can see, based on this is sort of like the key line in the Ruby script, which is sort of shows how much of a hack it is. This is basically how I find all the functions in a header. It's basically, this is the regular expression that we'll find, that at least for the naming convention we used, will find us all the functions in a header, and then I can use that with the parens in there to break out the function name, the return types, the arguments, and generate the code. So supermock will actually go through. For each function, it generates something like this. There's an actual function that's generated that lets you call the function name plus expect and return. So if the function expects nothing, then this expect and return would take nothing. If it returns nothing, then this would just not return. I guess an example would be like if you expect 3 arguments and you want to return some value, you would just pass those all in the argument list for this function. The way the CMock script would generate this function with the right number of arguments based on the return value plus the expected arguments to the function. And at the same time, the CMock would actually create then the actual mock file that stubs out all the tests or all the functions that were in the file being mocked. So when you call in your regular code, when you call functions in your class under test or your file under test, it would actually be calling the mocked version. So here's a unit test that uses the mocks. This is basically a test written in C, but it's not too unreadable. It's not too far removed from what you would do in a unit test in Ruby. It calls. This is the test for. This is the test for the function that does the main CAN communication loop on this board. And all we're saying is, that the loop, the conductor, which is what we called our file in our code that would do the sort of the main function loops, were called conductors. And they would call to a hardware function to ask if there's any CAN messages available, if it should do any CAN output. And this specific test is saying that when there's a new message available, it should then process that message. And we did this. What you can see from this test is the fact that we're not testing really the value, we're not testing a return value from the function. We're not testing, doing any kind of asserts, because everything in this conductor has actually been delegated out to other functions. And using the mocks has basically forced us, or it actually, I think it does sort of force you, if you want to write, have easy to write mocks and easy to maintain mocks, to delegate all your functionality out sort of to the edges of your code. Sort of a way to think about it is if your core functionality is at the top of a tree, and you delegate, everything you need to do down farther and farther, by the time you got down to the leaf nodes, the actual code you need to test that isn't using delegation to mocks is very small, and it can be simple, assert equals and, one-line functions, which is what most of our code actually turned out to be. So the way this works for mocking in C is you can't, obviously at runtime, easily replace function calls in C. So what we did is linking. Our build system, using rake, would actually, for every individual test, it would build a different executable, and for each of those executables, it would link in all the mock versions except for the one real file that's being tested. And then this binary was run in a simulator. For the unit tests, since they were testing sort of internal details and didn't need to, weren't testing the entire system, we were able to just, test this bit of code individually in a simulator. And there's one binary per test file, as I mentioned before. So the other part of our practices is continuous integration. It's another tool that we wrote in Ruby. It's something that we actually had already written for another project. It's something that was, just something we've written in-house. It's a very sort of simple Ruby server process that uses DRB to report status. We have old machines set up and around the office with web browsers that are hooked up to a WebWorks server that's reporting build status for every project in the company. So basically, should have taken a picture of it, but what we have around our office is monitors with little green boxes. Well, they should be green boxes for every project, just a big grid. And for any time a project gets checked in, the build server will be monitoring some version, check it out, and then run rake for every project. That's another reason, actually, why moving to rake for the C process was, a good benefit was I was able to hook into the build system we were using for our Ruby and Rails projects, where we've already got a build system that just always calls rake on every project. And then any project now that in our office that uses rake can easily be hooked into an automated build system. And so the unit tests are run in a simulator. The system tests are run on the build server itself. And these system tests actually run the actual production build on the real board. I think I'll just give you a little bit of overview of what the project kind of looks like. This is basically, I just want to go through sort of what the structure of the project directories are like. This is the top level directory of the project. We've basically got a rake file, source, and test files. Auto is a directory where we would keep the scripts for generating the mocks. We had a little library for parsing C code, which is just that crude function finder. I'll show you the Argent. Basically, all this is doing is, the way we'd call the Argent was that you would be able to specify the specific Argent file that you want to run. So a couple things we had generators we had for code was generating the checksum. One thing I didn't mention is actually for each of these builds, the actual code that was binary that was being built had to have a checksum calculated on it, so that when the board started up in the vehicle, it would check its own checksum and make sure its memory hadn't gotten corrupted. Generate the declarations. Here's the Unity code. So this is basically just doing a simple search to the file, and then just simply outputting the main function with a loop call to run all the tests. Here's an individual test function to run a test, and then we have a main down below, which just iterates through each different test that was found, puts in the line to actually call it. Here's the mock generator. I'm sure some people are probably curious to see this code for generating CMOCs. And it's really horrible code, actually. It's just a lot of ERB and a lot of text replace stuff. I'll get down to the even scarier parts. You can find funk magic. So yeah, here's funk magic. This is basically, it goes through, opens the output file, and just while it's reading the input file, is searching for the actual functions in there. And it's basically a giant if else, based on the whether the function is taking parameters, whether it's returning anything, it generates different mock functions. And this is actually at the same time, you can see it's it's also writing the implementation for the mock code. And the way the CMOCs are structured, if you're curious, is that it was actually there was a global struct that was automatically generated in this Ruby script that would hold pointers to every function call. Based on every function that was being mocked out, there was a struct that was created that would then hold pointers for it. And it would actually also let you store multiple mock calls to the same function, and it was using very crude dynamic lists in memory to, every time you called an expect, it would stick it onto the end of this list and reallocate the memory and let you track multiple calls. And we actually even started also tracking the order of calls for functions. So if you want to be able to enforce order of calling, you could actually do that too. Show you some of the test files, what the test code ended up looking like, what some of the other tests look like. I think I actually might have this in my slide later, but this is basically the main loop for CAN communication. You can see based on the system test or the unit test we had, it was just expecting, that we're checking for inputs and outputs, and then if they're available, calling functions. These are all delegations out, and this is it. This is this one file. This right here, conductor run, is actually like the core runtime loop in this board. And everything basically that you want this board to do is described here in very high level, very readable, and then it's all delegated out to other C functions. Yeah, one other thing too is this is basically the code that does the calculation for the battery level. And you can see it's also doing a lot of calls out to other functions in other files. So delegation is done, and I think there's about one file here that's a good example at bottom level. This is the table lookup code. And here's the kind of place where we aren't doing a ton of delegation, because this is sort of the final place where you get to the bottom and want to actually do the calculation of the numbers. But all the complicated stuff's already been done up to this point. And this code, is a pretty straightforward mathematical, assert equals kind of test where you can have a bunch of inputs and check the outputs. So here's a test of the actual calculation of the battery level, which is doing a lot of expects and returns, and it's also using this battery level table class, which is sort of doing the core calculation. I can show you what a leaf node test looks like. So here's the kind of test where we aren't using a lot of mocks, and we're just doing asserts based on a bunch of inputs. We know a bunch of given parameters, and we can know what the expected output should be for all that. And this is the rate file we wrote. There's nothing great to look at here, but one thing about this is it's very specific to this project. It does a lot of things of doing direct calls to the build system we were using, and the environment we had. You can see it's just a lot of specific directories. This is actually a project that was done, had to be done on a Windows box because the compiler was only available on Windows. So we've got a lot of sort of Windows paths stuck in here. There's specific host names and configuration options for this vehicle. So what were the benefits of this process? First off, the C code is clean. At least I think it's clean. It's, in my experience from having worked on other C projects, C++ projects especially, this is very clean and readable C code. The C code is generally dry. There's not a lot of duplication. There's a lot of delegation of functionality. And the mocking sort of forces that delegation, which also at the same time removes the duplication. And it's readable. I think I already showed this example file. Here's the main communications loop. The binary that's actually being tested is the binary that's actually deployed. There's no magic build with magic hooks for testing. So what you're actually putting on the board on the system tests in the end are what are actually going to be deployed onto the vehicle. We had system tests that were readable by the customer, and they were very quick to write. The unit test would actually testing behavior of the code, not just the inputs and outputs. And the unit tests and system tests were actually easy and fun to write. The customer was happy with the output. They were able to see a new feature system test be written right in front of them while they were sitting there. And the developers were happy writing this code because we got to use Ruby. We got to do all the practices we wanted to do. And that was it. Any questions? Yes.
What sort of industries have really been excited about using Ruby?
This industry is actually it's industrial. These vehicles are being built for industrial plant use. We've also been working with a customer that creates color management hardware, and they have devices that measure and scan color, and it's also all being done for factory and lab work. And it's kind of a place where they have this hardware that's being custom developed in-house, and the deploy costs or the debugging costs once it goes out to the customer are so big that the time that is spent creating these Ruby tools has a lot of value to them because they know that there's going to be less code going out with bugs and less changes and revisions that have to be made. So for us right now, we've just been focusing. It's been very much sort of an industrial market for this embedded work. A lot of the devices that we've been doing aren't actually consumer oriented. I guess there's one difference is that the industrial stuff is usually a little bit more expensive, and so they probably have there's a little more time and money spent to make sure that things working right, versus like consumer hardware where they might feel that it's cheap enough where they can just throw out a bug isn't a big thing if the device is cheap and throw away anyways. I don't know, but it's just also the part of it is that the customers we had have been industrial. Any other questions? Yes.
Do the vehicles respond to any manual direction, or is it all in response to your remote requests?
Oh, these vehicles are actually respond to manual control. There's actually on all these vehicles, there's a button where an operator can run up to it and hit it and stop it and put it into a manual mode, and there's actually like a joystick on there to control it. But the joystick actually injects CAN messages onto the bus as if it was just another board, the computer telling the vehicle where to go. And so when we worked on, for example, the speed control board, it would have to be able to take speed commands from either the vehicle computer or the joystick. And so yeah, these vehicles can be manually controlled, and it's the same boards and software being used for that. Any other questions? All right, thank you very much.